Okay, we're here on the last page. It says find the measure of one angle of a regular 15 gun. If it's regular, all the angles are the same. All of the exterior angles here will be the same. So if I just take 360, which is our sum of exterior angles, and divide that by 15, I will find the measure of that angle. So let's see, what is that going to be? When I divide 15 into 300, it goes 20 times, and then 24. So that's 24 degrees. So then this angle here will be the supplement of that. So 180 minus 24 then is what? 156. Okay, so 156 degrees. I should write 180 maybe minus 360 over n. That's the formula that we use. All right. Prove that a regular polyhedron cannot have a defect angle of 72 degrees. All right. Well, for a regular polygon to have a defect of 72, they would all have to have 72. So I would have 720 degrees as the sum of my defect angles, and I'll be dividing that by 72 degrees. So I'd have to have a 10-sided regular polyhedron. So this is a proof that we're going to do by indirect means. All right. So statement to be proven is really the first thing we do. Then we assume the opposite. Assume that there is a polyhedron. Okay, that's the 3D figure again, with 72 degree angles. Alright, so that's our assumption, and I've organized this very poorly. But step 3 then is basically going to be this part of the math right here. If that's true, if so, there are 10 vertices. Okay, well, there are only 5 regular polyhedra. None have 10 vertices. Okay, which is a contradiction. Okay, it must be boring to watch me write this, but that is a contradiction. So this one doesn't have a lot of math. I'm sure the one in the test will have something we have to do at least a little bit of math beyond this. But if you study the Platonic solids on that one page in our book, you'll see that there's really only the tetrahedron, this shape, and you could sketch them all out or whatever, but that one has 1, 2, 3, 4, 5, 6. There's the cube, which has 8, okay, and the other ones have more. The tetrahedron is the simplest one. Actually, this is an octahedron. It's a square-based pyramid that's joined. The tetrahedron has just 4 vertices. All right. So none of them have 10. So that's the contradiction. Therefore, step number 2 is false. So step number 6 is okay. Number 1 is okay. I've run out of space there, but you would have a little bit more time, obviously. I'm doing this on the fly. But that's the way the proof by contradiction works. Assume the opposite, prove that that's ridiculous, and then you're left with the original statement being the only possible reason. Alright, here's our final one. Using a little bit of analytic geometry, we're going to plot this and figure out what it is, and then verify it using math. So I'm going to do this fast. Negative 1, 2, 3, 4, 5, 6, 7. Positive 1. There's K. Then 3, 12, 3. And then it's 3, 6, 9, 10, 11, 12. I'm not going to let that throw me off. It's up there. There's L. M is 13, so that's 3, 6, 9, 12, 13, and 2, about right there. There's M. And then finally N is 3, negative 9. 1, 2, 3, then 3, 6, 9. All right. So what shape is this? Okay. That doesn't look very good to me. I better check this. If you get something like this, double check your math. -7, 1, that looks good. 3, 12, that actually looks okay. 13, 2, that looks okay. And +3, -9. Did you watch me do that? That must have been like torture. +3, -9 is right here. Okay, so if it looks sort of wonky to you, double check your math and your plotting. This looks a heck of a lot better, and that's n. All right. The first thing I would do is all of the slopes. So I'm going to do rise and run, then run and rise, run or drop and run, and I'm going to just make like a rectangle around this. That I think is the most effective way to do it. If you use the arrow method here, where I just look at the change, that's a rise of 11, and it's a run of 10. 11 over 10. Then from L to M, that's a rise of -10 and a run of -10. All right. So right there, my slope is equal to 1, and my slope here is equal to 11 over 10. So close, but that is not a right angle. Not perpendicular. All right. Because the slopes would need to be exactly opposite reciprocals. Why do I have it being negative? That's a negative slope there. That's clearly -1. So I drop 10, but I go +10. So again, you make mistakes, but you catch yourself because that has to be a negative slope. This has to be a positive slope. So from n, going back to m, it's rising 11, and it's running 10. So that's a slope of 11/10. So right here, this is a slope. So these are parallel. So it's a trapezoid at least. Let's do the last one from -9 to 1. That's a rise of 10. And it's a run then of from 3 to 7. That's also 10. So this is our -10. So this is also -1. Okay, so these guys then also are parallel. So this is a parallelogram that is not right angle, so it's not a rectangle. The only other thing it could be would be a rhombus if it happened to be exactly the same lengths. But one of the benefits of doing the slope is that if I do the distance formula, it would be 10 squared and 11 squared, and that's not going to be equal to 10 squared and 10 squared. So these are not the same length. These sides are slightly longer than these sides. So the only possible word for this is a parallelogram. All right? And I'm not even going to write it all out, but it's because the opposite sides and only the opposite sides are parallel. Verify one property. The thing that I would verify with a parallelogram, right, arguing the extreme, that these diagonals bisect each other. So I'm going to do the midpoint formula here. Find the midpoint of K and M. Go up to K and M and average their coordinates, 13 and -7 for the x's. 13 plus -7 is 6, cut in half is 3. 1 and 2 added up make 3, cut in half is 1.5. Double check that I did that right. K and M. 2 and 1 is 3, cut in half is 1.5. So that's that midpoint right there. Should be that when I do L and N, I get the same exact midpoint. So it's getting a little bit obscured here, but 3 plus 3 is 6, cut in half is 3. And then 12 plus a -9 is 3, cut in half is 1.5. All right, so I might write that out. I might do the whole midpoint formula out. But in the interest of time, I'm going to stop that right there. There you go.